Okay, when it comes to three-phase wiring, there's really no wrong way of wiring the 3 hots. The biggest thing you want to make sure is that you get the ground in the right spot, because you don't want to run the voltage to the ground, because you'll just go to a direct short and you'll take out your breaker and a lot of other things. So I'm putting the ground wire into the green screw here. Good and tight. Okay, now when it comes to the other wires here, this is braided wire. It's really nice wire because this is a SJOW, I believe, cord. And I'm just going to stick the black wire in the first phase here. Okay, so now I have the 3 wires coming out for the 3 phases, phase 1, phase 2, phase 3, and the ground. So the output is hooked up. I'm going to do the same thing to the input side. The manufacturer has done a really good job of identifying that this is for 200 to 240 volts plus or minus 10% with this little sticker here. So I'm actually going to put it here just to keep it. And I've looked in the owner's manual on this one. It calls for the 240 volts or 220 to 240 volts single phase is for L1 and L2. So I have the ground, L1 and L2. As far as the black and white, it doesn't matter because they're both hot. Okay, I've got the ground in. Make sure you get these connections good and tight. That's really important. You don't want any arcing. Okay. So I have single phase power going in, 3-phase power going out. Now I'm going to go grab the motor that I'm going to use to run off of this, and we're going to go through the setup. Okay, so the drive is powered up yet. Let it running for a few minutes here, make sure there's no magic smoke, and that's all good. The cooling fan hasn't even started yet, so that means that it's still running nice and cool, basically because it's just sitting idle. So the one thing is, on this particular drive, you can make it work off the keypad, but you have to put a jumper in the terminal 1 to terminal 2 on the control terminal, basically letting the drive know that it's just basically a communication from the keypad to the software in the drive that you're actually using the keypad. Now on the more expensive models, like the older 15Hs and the H2s, it did that internally just by going in the parameter. But even though I've told this in the parameters I want to run off the keypad, you still have to have a jumper from terminal 1 to terminal 2. Turn it off. And it coaster, actually it ramps down to a stop. Now there's other parameters in here as well that I can change as far as how fast it ramps up and how slow it ramps down, things like that. Okay, so we're going to go into accel time and decel time, and that is parameter 10. So I'm going to go into enter programming. So this is on 5 seconds. I'm going to change that down. We'll do 1 second. And parameter 11 is decel time. It's 5 seconds. I'm going to do 10 seconds just for the sake of the video. It's already up and running. And it's ramping down. Okay, one other parameter I want to touch base on here is parameter 21. I'm not sure how well you can hear the audio frequency of the motor that's driven off a VFD, but one of the things that you can tell by a motor driven off a VFD is they kind of got like a high-pitched whine to them, and it's a consistent whine. Some people it's kind of annoying, some people can't really tolerate it, and some people don't even hear it at all. But I'm going to show you that that can be changed. Right now it's at, so this is at 16. That can't possibly be right, but I'm going to go down to 4. You should really be able to hear this. Oh yeah, you can hear that, providing it's not messing with my wireless mic. Okay, so we're going to go up. This is 8. This is a quite common operating frequency. Let's see here, we're going to go 16. This is where the factory setting was. Here a little bit, not bad, which really surprises me because on the Balder, we'll turn this off. On the Balder 15Hs that I have, at 16 kilohertz, they're like silent. You can't even hear the whine of the VFD. But this one goes up to 32, so I'm curious as far as how much it gradually changes. I'm at 24 now. Should be silent. Yeah, it's gone. Very, very, very faint on hearing that. Going to the last one, I think, which is 32. Yep, 32. Enter. Okay, so it's running silent, but the one thing I want to make you aware of is that when you start messing with the PMW, what do we call it here? A PWM frequency, post-width modulation, also known as a carrier frequency. There's a disadvantage to running a VFD at a very high PWM or carrier frequency. Reason being is that the higher you run that, the more quiet the motor is, the harder it is on the transistors within the drive. Typically, manufacturers will derate the drive if you run it past a specific carrier or kilohertz frequency. If I were to probably read a little deeper in the manual, I would say probably anything after 16 kilohertz probably could derate the drive by a certain percentage for every variation above that. But you know, 16 made a little bit of noise, but on my 15Hs, I know I've tried them at like 15 and they were pretty much silent, so I was surprised to hear that this one was still a little bit there at 16. But we're going to take it back. We'll keep it at 16 for the time being. Okay. So that's kind of your basic setup, and the nice thing with this one here is that you can use the up and down arrows to actually make it go up and go down. So I'm going to bring the camera a little bit closer so you can kind of see as far as the different parameters within this. Okay, so some of the common parameters that you want to make sure that you have set up is the motor nameplate amperage, the motor nameplate RPM, the motor nameplate frequency, and then that's pretty much the necessities for the motor, because what it'll do then is once you have like the motor frequency, the rated RPM and rated amperage, the drive will work within those parameters, so it knows that if the motor, for example, exceeds a specific amperage, if say the nameplate calls for 2 amps, and the drive exceeds 2 amps, it'll act as an overload protection. It'll actually shut down the motor itself, and it'll show up an indicator here as a fault. those are the three critical things you want to do. And the other thing is too, is just make sure you have it set up so that you can either run it remote or you can run it off the keypad. If this was a NEMA 1 enclosure, I could just run it off the keypad, but because it's an IP20, it needs to go in an enclosure. So I would actually run a remote start and stop switch for that. But so on the display here, basically on this particular model, it shows it's in the stop mode. And if I push start, it shows the RPM it's putting out. Shows it's pulling 1.1 amps when I push the enter program button. And it shows it's running at 60 hertz frequency or 60 hertz. And we're back to 1800 RPMs. This particular drive actually goes down to a ramp time of 0.0, so it basically is, down to 0. And because this drive is so oversized for the motor, the drive doesn't even fault out. It doesn't even blink. It just automatically has the motor up and running in a split second, literally. Even running it down fast was the same way, but I don't recommend doing that. The nice thing about the VFD is you can actually use these as a soft start as well. Here, for example, let me go into parameter. 10, I'm right at where I need to be. I'm at 3 seconds. We're going to boost this up to 10 seconds. Oh, I'm at 20. Let's not do that. Okay, and I'm going to do the ramp down as well. It's at 1 second. I'm going to do 10 seconds as well. Enter. All right, here we go. And as you can see, it's up and running. We're going to push the stop command. And that's the real basic operation of a VFD, just for real simple starting and stopping. I'll actually go and change that start to the lowest setting, which is 0.0. Alrighty, here we go. Just as if it was a direct online 3-phase start. I'm going to show you the same thing in the stop. Now, I wouldn't recommend doing this, especially if your motor horsepower is pretty close to the drive rating. You would go into a fault condition, but for the demonstration of this video, I'm going to show you. You can pretty much make this thing stop on a dime. I'm going to go to 1 second here first. I haven't done 0. Actually, I'm going to do a half a second. All right, here we go. Off. I got a 0 volt. It's an overvolt. Reset. All right. So we're going to move that up a little. We're going to do it to 1 second. See if it likes it this time. Yep, 1 second it'll do it. If I just had the motor on this blower not hooked up to the blower itself with a belt, it probably would have stopped it in a dime. But because it's got a little bit of a load on it, the drive realized that it couldn't quite stop all the momentum. Even though this is a pretty easy pulling load, it still couldn't do it. But let's try that again here. So starts it no problem, stops it no problem. Okay, like I said, I really wouldn't recommend doing that. But what I'm going to do next is I'm going to play around with, there's what they call a DC injection braking. I'm going to go find the parameters. I'll turn the camera back on and I'll show you where that's at. That's kind of another cool feature, especially if you got a load that has a high inertia behind it. You can use the DC injection braking to slow that load down in a matter of seconds versus, maybe a minute or minutes. Okay, so I've kind of played around a little bit with the DC braking offline. It actually doesn't perform the same as some of the other ones, but if you had an application to make the drive stop, you could make it stop. I also have enabled what they call an energy saving feature, and basically what it does is it tries to minimize the overcurrent or the over excessive voltage drop and amperage rise, such as inrush current on the motor. So it actually kind of winds up a little bit differently. I know well you're going to hear this, but we'll give it a shot. Kind of like a soft start almost. And I do have this set up for a 0-second soft start, but I can also make it stop pretty quick in the same manner. I'm going to go back to, oops, 11. I'm going to go back down to, let's do 1 here. Yep. Somehow or another, I managed to make this thing whine a little bit. Let's try this again. I don't know how you saw that, but pretty much stopped it on instant. Let's go into, remember how I tried that before and it would go into a fault out? Well, because I have the energy saving feature on, it works a little bit better. Now we're going to go to 1 second. And now you can hear it, I've made the drive a little bit mad. It had to work and the cooling fan has kicked in now, which it won't run very long, but it's doing what it's supposed to. So in this case, the DC braking is working, and the also has the energy saving feature as well. So it's not an initial push on the drive to make that drive the motor come to a complete stop. So that's kind of the nuts and bolts, real basics of a VFD, basic functions. If you have applications where you need to slow a load down in a fairly quick hurry, this will do it. If you have a really high inertia load, you may end up using what they call braking resistors, which is an optional kit for a VFD. Basically what it does is there's a couple terminals down here that are actually blocked out, but it's basically a B plus and a B minus. And what is it? That's for your dynamic braking and your braking resistors. So what happens is, in the event a motor is trying to be slowed down with DC injection braking or dynamic braking, there's excessive voltage buildup in the capacitors within this drive that actually need to dissipate excess voltage someplace. And usually what they do is they dissipate in heat. But because of the heat sink on the back of the drive isn't really big enough, you go with the optional braking resistors, and basically it's nothing more than a heat sink where it just pumps all that extra voltage into it and dissipates it off in heat. So very common on high inertia loads that are hard to start and hard to stop. Let's try this once more. See, I made the drive angry again. But it was doing that basically because I'm using the DC injection braking, and because I'm trying to slow the motor down in such a hurry that extra voltage is being dumped into the heat sink, and therefore the heat sink's getting warm, and then the little cooling fan is going to cool the heat sink off again. So that's what the cooling fan's designed to do, is to basically keep the heat sink cool so the drive stays healthy and runs cool. And now it quit again. So let's try it once more. See, I've made the drive angry. So anyways, hopefully this video was somewhat helpful. I'll probably do more and more videos on VFDs, maybe not necessarily this one, but I'll kind of go over more of the functions. But the one thing that I did not really talk about, I should really talk about, kind of get understanding as far as how a variable frequency drive works. So we'll kind of go into that here. Okay, so we'll try this again here. I did make it mad this time. So, all right, so that kind of takes up the rest of the kind of the series here of the variable frequency drive. I'll probably do more on this particular topic based on responses and more questions that come up. Like I said, the variable frequency drive is a very handy tool for three-phase application where you have single-phase power. So it's one of them things that you know, can work very well in a lot of advantages, but you got to know what to expect out of it as well. Okay, the one thing that I wanted to point out that I failed to talk about at the very beginning as far as the basics of the VFD. I didn't explain as far as how a VFD actually works, as far as what's the magic of it. Basically, you're taking AC input power, single phase or three phase. You're converting into DC power by the means of DC bus capacitors, and it's being rectified back into AC by the means of IGBTs, isolated gate bipolar transistors. What they do is they allow you to change the frequency and the voltage to the motor while keeping the motor satisfied. There's a voltage to frequency ratio that it seems pretty steady for the most part, but basically that's what's happening is you're converting AC power into DC and then converting it back into AC, changing the sine wave so that way you can actually change the speed of the motor by the means of the voltage and frequency. So that's kind of it, really, how it works. Don't be intimidated by them. They're very simple, pretty easy to wire for the most part. Like I said, the biggest thing here is you want to make sure that you have the owner's manual, because without the owner's manual, you're really guessing, because there's a lot of different parameters in here. This one, just in the basic parameters, I think goes up to 37, but you know, don't be intimidated by it. And the other thing to keep in mind too is that these are also usually available just in strictly single phase input, and some of them are available from 110 to 120 volt single phase input as well. Those you cannot run 220 to 240 single phase in. If it specifically says 110 to 120, you have to use the 110 to 120, which is just a standard wall outlet. Typically you'll find those up to probably 1.5 horsepower, and that would be it. Other than that, everything's going to be 220 to 240. And like I mentioned earlier in the video, most of these VFDs that have a 220 to 240 volt three-phase input AC, you can run them on 220 to 240 single phase, but you might have to derate the drive. Once again, you can make a three-phase motor, a larger three-phase motor, work off of VFD. You just have to make sure that you have the VFD sized accordingly. You can always go big on the drive, but you don't ever want to go too small. Reason I say you can always go big on the drive is because in the drive's parameters, you can change the motor information as far as the motor nameplate, amps, voltage, and frequency. For example, this is a 3-horse drive and this is a 0.5 horsepower three-phase motor. So what I did is I changed the motor nameplate rating inside the drive here to, I think it was like 4 amps for this 0.5 horsepower motor. And if the motor ever came overloaded, the drive would recognize that and it would shut down. So you can always run a large drive on a small motor. Unlike a rotary phase converter, that doesn't work very well, just for the simple reason you get what they call over voltage, and then the motors run hot. So it's not really wise to have a 10 horsepower rotary phase converter running a 0.5 horsepower motor. It's just, first of all, it's not economical. Second of all, it's actually really hard on that small motor because it's got a lot of extra voltage going to it. So it's one of those things to kind of keep in mind, and that's where the VFD would probably really come into play for a lot of applications. So I hope you guys enjoyed this video series, and I'll probably do a little bit more follow-ups on VFDs, get a little bit more advanced, but I wanted this video series to be more basic, just to get an understanding as far as how they work, how they set them up, what the principles of them are, and just the simple ease of use. So hope you guys enjoyed this video series. Questions and positive comments are welcome. All right, guys, thanks for watching.